Anyway, so Artyom is first up, talking about DNS security issues and how to basically better manage those. So let's give him a warm round of applause and welcome him, and let's get moving forward. Thank you very much.
Good morning. First of all, let me say thank you for showing up so early after midnight social. Wasn't expecting so many people coming up. If I was you, I wouldn't, by the way. First of all, a disclaimer. What we're mainly going to talk about are the issues related to maintaining a DNS zone via an authoritative DNS server. Some issues are also kind of applicable for recursive DNS server. So we'll see, but the main focus is DNS zones and authoritative servers. So let's start with a bit of history. Back in the time of dinosaurs, which was like 80s, the humanity was struggling for a solution to a civilization-threatening problem of name resolution. On contemporary computers, you can still spot an artifact from that distant past, which is called a host file. Host file is essentially a mapping between an IP address and what is supposed to be a handful of host names. So if you wanted to resolve a host name, you can just read this file line by line until you found what you are looking for, right? And the correct mapping with an IP address. It worked for a while, but the issue is if your internet consists of a large number of computers, and I mean really large, like 1,000, you easily run into all sorts of troubles maintaining and supporting all those files in case a new network service is fired up. Thus, a network protocol was born, UDP-based at that moment, with clients and servers and stuff, but the whole purpose of this protocol was, again, simple, and very like to this intentionally wrong pseudocode. So it was just a simple conversion from a string, which is a host name, to a 4-byte integer, which is IPv4 address. Some other functionality was also built into the protocol, but except for few cases, it was all just required for the protocol itself to run. And the main purpose initially was like that. Then, a bit less than 10 years ago, World Wide Web appeared, and enterprises have started to conquer it. World Wide Web imposed new requirements for DNS protocol and kept doing that. New applications like load balancing, geo-balancing appeared and were then refined with more thorough approaches like policy-based, ASN-based balancing. We'll discuss it a little bit later. Next, enterprises wanted business continuity and redundancy. So they opted for DNS-based failover. More and more functionality was added via extension mechanisms like eDNSO, client subnet, and more. Next, IPv6 has arrived, and a lot of security stuff was being started to be implemented into DNS protocol with DNS, SecDane, CAA, and so on. So now, there are such a lot of features and opportunities built into a DNS protocol so that if you are even not using them currently, you will start doing it at some point in time, or else your competitors will do. And here is our problem. How should an internet company maintain its DNS infrastructure? Well, there are basically two options. Either you can run it yourself, or you can outsource it to some kind of third-party provider. With each approach, there are more questions to it. If you're doing it in-house, then you need some kind of a software server product, which will essentially do DNS responses for you. And if you're outsourcing it, you need to choose a service provider because there are just plenty of them available. So here is our problem statement. Let's figure out. Starting with option 1. How do we choose a software product at the point where the overall requirements are not still very clear? The protocol is changing, the world is changing, and but I need to choose something. Naive approach would be the service software should be scalable in order to handle all the load your marketing department could bring to you. B, it should be feature-rich in order to handle our future suggestions and possible requirements. Let's start this way with scalability. Back almost 5 years ago, we have carried out a complex benchmarking for different DNS service software releases. There was a comprehensive list, which is on the slide, of the products to test, and we brought some hardware decent at the moment for that. All the software was in vanilla state without any third-party patches or plugins. Our purpose was purely academic, in order to find out who runs better code with better hash tables and stuff. So this is why we've mixed authoritative servers with recursive ones. And for the authoritative thing, we've generated 300 zones for testing purposes. And for caching resolvers, we've kept pretty much the same amount of data in warm cache. We've done our benchmarks, we've got our results. I'm referring to our previous 5 years old presentation for details. Here is a link on the slide. And when we've shared that, the question everyone kept asking us was, guys, where's bind? Well, during preliminary testing, a bind appeared to show results so disappointing, in most cases completely indistinguishable from the X8, that we've decided to skip benchmarking bind at all. However, 5 years ago, or 4 years ago, when we've decided to repeat our benchmark to see if anything has changed in the world, we've added bind to that. Here on this slide is the amount of responses served as more and more queries per second kept coming up to a number of 2 million at the right side of the slide, by 3 different servers, namely bind, NOT, and NSD, under 3 different conditions. The higher the graph is on the right side, the better the results. And ladies and gentlemen, here is bind. Regardless of affinity and other configuration options, bind has failed to catch up pretty soon. At the stage, there were about 400,000 queries per second on our hardware. And this is not only our observation. Just for a sanity check, here is another test run by authors of DNS server called NOT. Note that the scale has changed somehow. On the y-axis, there's now not the exact amount of responses returned, but the percentage of successful responses. So the closer to 100% on the right side, the better. Here, at a rate of 1 million queries per second on a server dedicated for this very task, bind fails to answer 1/3 of requests. And this is when you have no DNSSEC, because when you turn it on, the results are a lot worse. Bind starts failing requests almost from the very beginning, and at a rate of 1 million queries, it doesn't handle even a half of requests. This is not good. Bind is de facto a standard DNS software, right? It's widely used on the internet, and it appears to have all sorts of scalability problems. Yes, of course, there always are solutions for scalability problems. For example, like you can always land a server farm roughly equal in size to a soccer field, fill it with backend servers, and set up some reverse proxy in front of the farm. And that will pretty much do for most of scalability problems. For example, this way you can really do quick handshake in user space or stuff. But when we're speaking of a simple task like DNS, this pretty much looks like an overkill. OK, our next solution is to choose some other product instead of bind. But bind is de facto standard again, and all its competitors have much less customers, which raises all sorts of questions like, who maintains that? What is his motivation? Would they keep like backward compatibility in case they get bored of supporting their old code and decide to rewrite all the stuff from scratch? How reliable is it? Is it scalable for all the purposes, or its authors are just targeting their, or a couple or a handful of use cases, important or interesting for them? How will it be scalable under other conditions? How well is it supported? What is the SLA for fixing bugs? Regarding bugs, are authors aware of contemporary security approaches? Well, what's with fixing vulnerabilities, bug bounty, etc.? Because if there are no security advisories published for a software product, it doesn't mean its authors are good at writing software. It might as well mean they are bad at writing advisories. And again, what features are on the product's roadmap? So here, with all these issues, we always tend to get back to our requirements. Maybe they are just excessive. What is this feature set we might want? Is it really big? And how scalable a good old DNS server should be? Because in its core, a DNS lookup is quite a simple thing. Here is the Facebook page of our meeting. I've hard reloaded it a few times and collected traffic dumps. Back in the time of dinosaurs, you could easily expect like 2 to 10 DNS packets in the dump, but today we have all sorts of subdomains, CDNs, and counters and stuff. So an average Facebook page makes about 50 DNS queries to load, which accounts for 100 of packets here. But when you're just counting packets, it's still 1/8 the amount HTTPS services generate. And each DNS conversation is rather simple and straightforward. Like, you have a query which is 30 byte long plus all the headers. Then you get an answer which is 45 bytes long plus all the headers, and that's pretty much it. So apparently, DNS isn't rocket science, right? Well, it's not, when we are talking about the type conversion thing we've started with. In theory, there's no difference between theory and practice, but in practice there is. What if we want more? Let's start with geobalancing. It's a widely used method, as it's so appealing, right? To reduce the latency between network clients and like web services by looking at the IP source of a DNS query and returning an answer with an IP address which is as close to client as possible in terms of geolocation. Say, here's an example. Let's say you have a customer in South Korea and you have 2 servers set up, one in Japan and the other one in California, so you probably want your customer to go towards a Japanese server, right? Sadly, there's no country data present in an IP packet, so you should use a proprietary database from some vendor here to map an IP address to a geolocation. However, reliability of such databases for that particular task is questionable, to say the least. Here is a simple example. I've took the demo on one vendor's website and submitted Google public DNS address. Here's what's returned to United States. Sorry guys, but 4 8s are anycasted. They are not in United States, not in Europe, not in Singapore. They are in each of those locations. And another funny thing, by the way, is that the database not only returns the country, it also gives us GPS coordinates. Where's that? Let's have a look. Wow, in the middle of Cheney Reservoir. How's the water, gentlemen? So this is wrong. Actually, there's pretty much more to it. All those databases, regardless of vendor, I'm not blaming MaxMind here, have this owner location versus actual geographic location dilemma. What would you return? They are generally unreliable for anything except raw statistics. There's a long story, by the way, about those GPS coordinates. Follow the last link on that slide. But the overall idea is the database does know that the results returned are inaccurate, sometimes intentionally inaccurate, yet the database API doesn't give us a clue to that. No warning, no error. This is just one of the long list of issues. I'm not blaming MaxMind again. All those databases are all the same. I've tried a lot. Vendors, for instance, are used to import data from regional internet registries databases, where the information is often inaccurate or outdated. But probably the main issue with geobalancing is that if you have a server in Japan and a client, a customer in South Korea, the traffic between them doesn't necessarily go through Pacific Ocean. It could as well go all the way through Atlantic. Because once again, as I've said before, there's no country data in an IP packet, and there's no geography on the internet. There's just network topology. And there are no countries. There are just autonomous systems and their mutual relations. With that in mind, some DNS operators recently started offering more granular approach to balancing. Here, for example, is NS1 and their netfence filters, which can be used to subsequently refine answer policies for different AS numbers and prefixes. So in case your South Korean users start complaining about increased latency, which might be the case today because there are Olympic Games there, and a lot of your customers are probably there, you can simply add specific policies for problematic Korean prefixes. Problem solved, management is happy. So geobalancing and prefix targeting may be extremely useful for some enterprises. The issue with that, of course, as a matter of fact, is this all adds great to a computational complexity of a DNS answer. Next, dynamic configuration. This is about how do you deploy changes in DNS configuration. Here's an example of how it was in Spotify like 5 years ago. There was some chat in an internal messenger, flooded with off-topic, as a matter of fact. And from time to time, an engineer in duty shouted in this chat, "DNS deploy!" This meant that he is now going to deploy changes in their DNS setup. This desperate shout itself served two purposes. First, everyone got notified that some configuration changes are ongoing, so if anything goes wrong, they know where to seek revenge. Second, it served as a mutual exclusion, a locking mechanism. Of course, this approach allowed for all sorts of troubles, and Spotify guys are brilliant. They are not doing this anymore, and neither should you. DNS isn't a static configuration file anymore. This is essentially an API for configuration management systems and different applications, service provisioning, statistics and monitoring, policy management. All these are tasks for this API. An enterprise will want this sooner or later. Working with DNS old style with manual deployment and human error thing isn't a contemporary way to do that. Next on our stage, failover. If you have two servers in your DNS-A record and one of them goes down, you want it to be taken out of DNS rotation. For this, you need some kind of a monitoring tool again, which then reports to a DNS API we've discussed before. There are issues with DNS failover. Here's a graph of HTTP requests towards a server which was taken out of DNS rotation a quarter after 10 p.m. on the left of the slide. The TTL of DNS record was 120 seconds. As you can see, 15 minutes ago, 1/3 of traffic was still flowing towards the server, which was at that moment supposed to be down for a while. Only roughly an hour ago, the traffic finally stopped flowing. And all the square between the blue line is customers who would have been lost for a website in case of a real emergency. You can somehow fix that by reducing your TTL, time to live, of the DNS record to figure like 20 seconds. But this way, your traffic will be easily 6 times it was before the change. Next to the security, as we've discussed before, you need to figure out how the author of your DNS software handles vulnerabilities, how often patches get released, what's the policy of, on security advisories, etc. Another security issue is DDoS. First, DNS is, once again, UDP-based by design. So it's more exposed to volumetric attacks like amplification and so on. You need to use some kind of effective line rate challenges or handshakes to verify the source IP address of queries, not to respond to a spoofed traffic. For high-level attacks like water torture, you need some kind of analysis, statistics, and blacklists. And again, blacklists are ineffective without those challenges, as DNS traffic can easily be spoofed once again. To handle large attacks, you'll need an unencasted network. For DNS, it's not an option or suggestion in 2018. It's a must, because DNS attacks are cheap for an attacker and completely disastrous. There are also other things like DNSSEC, DNS over HTTPS, and so on. There are almost 200 RFCs written and related to DNS. So now, homegrown DNS starts to look pretty much rocket science. So now, what about service providers? There are plenty of them. I've outlined a few on the slide. Sorry for not putting your favorite provider on the list. I have a slide only of that size. However, the question stands, how do we choose this way a service provider? But this way, we have some good news. A good news is that apparently you don't need to choose. Introducing SRTT, which is a smooth round-trip time. This is a mechanism built into resolving DNS servers, a lot of them, and already deployed in most small office, home office, and even enterprise networks, mostly accidentally, by the way. NS1 study suggests that though only like 50% of DNS resolvers on the internet have it, those 50% of resolvers actually account for up to 90% of internet traffic. SRTT is intended to help running a lot of authoritative name servers simultaneously for a zone, benefiting from the combined coverage of all of them. If there are, say, 2 name servers for the zone, a SRTT-enabled server will query both and then use the one which responds faster in order to reduce latency for a DNS client. Here is how it works. Are you familiar with boxplot? Please raise your hands. Oh, good. Meet boxplot. A boxplot is a method for graphically depicting groups of numerical data. In our case, this will be the response times of DNS queries through their quartiles. The bottom and the top of the box are always the first and third quartiles, and the band inside the box is always the second quartile, which is a median. The ends of the whiskers are always minimum and maximum of all the data, or something closely to that. Here are Stack Overflow's DNS measurement in New Zealand. Stack Overflow operated 2 DNS operators at the time, Amazon Route 53 and Google DNS. Apparently, Route 53 has a point of presence somewhere close to New Zealand, and Google hasn't. So if you replace route 53 with Google, you'll get complaints from users due to heavily increased latency. However, what if you don't replace but add Google in line with route 53? Will there be any drawbacks for the DNS performance? Here's the result in green. As you can see, a combined solution performs much better than Google. It's roughly equal to route 53. So adding in even a heavily underperforming DNS operator doesn't affect latency in a bad way. What is more funny, the combined setup, despite Google's inefficiency in New Zealand, performs even better than route 53 alone. So the bug splat is lower. This is probably because there's a couple of locations in New Zealand where route 53 performs really bad, probably because of ISP relations we've discussed before. In those locations, due to SRTT, Google takes over. So if you run two solutions simultaneously, you benefit from both solutions in the most marvelous way. So here's how you can choose a DNS provider. Just pick a few. The more you have, the better. In my belief, up to 4 or 6 will be just fine. This way, in case, by the way, you are paying them for the real traffic usage, it's easy to track down and replace the underperforming ones. Because those underperforming are those who will service less traffic, so those whom are paying less. Having multiple providers also helps with operational issues and failures and maintenance windows on behalf of your providers, all them being DDoSed or anything else. There's a mechanism built into DNS for distributing zones, but it's, to say the least, not that feature-rich compared to our current requirements. So you'd better stick to providers with nice and convenient API. So now, I hope that now with all this in mind, whether you're an enterprise or a network operator, you'll be able to build your DNS solution in a better way. Questions?
Hey,
Oh, hi.